Is this thing? Yes, never mind.
Hi guys, how's it going? Nice to see you all here on a Monday. I know it's a long weekend, but bear with me. This weekend, if you guys know this going on Saturday, Sigma Alpha Mu, which is one of the new fraternities on campus, is having our first annual amateur stand-up night, which we've called Humor for Hearts. Basically, anybody who thinks they're funny enough to do stand-up for 5 minutes can come out and audition for the show and get on stage for 5 minutes, 10 minutes, whatever, and do stand-up. Admission is open to the general public. It's $3 beforehand and $5 at the door, and all proceeds will be going to the American Heart Association. We also have 2 local comedians coming down from CSU, so they're going to be in the act too. And we also have JD Sidley, who's a professional MC. He's coming down to MC the event. So hopefully we'll see you guys out there. It's going to be a lot of fun. It's going to be this Saturday, March 29th from 8 o'clock to 11 p.m. at the spot. And if you guys want to audition, you can contact me, which is the phone number at the bottom if you want to audition. So hopefully we'll get to see you guys out there.
All right, you guys got any announcements? Is this thing? Yes, okay.
Hi, everyone. As you can see, the SI sessions are like normal, Monday, Tuesday, Wednesday. Wednesday is the exam review, 7:30 to 9:30. We will be posting problems ahead of time, so the problems should be up tomorrow, by tomorrow night. Strav will probably send out an email, okay? So expect maybe 10 to 15 problems on acids, bases, titrations, buffers, KSP, and KF. So hope you guys can make it to that. The practice problems will be posted sometime tomorrow. And she'll probably send out an email, but check Blackboard for those.
Just to reinforce that, there's an SI session tonight, and last year this was the hardest test by not just a little bit, but by a lot. So you might want to, learn how to do it, because I was talking to a few of you, and y'all weren't terribly pleased with your last exams. So, come do chemistry. It'll be fun.
Sit and be patient. My gosh. You'd think you were a senior or something. No. It's not working. Well.
Justin and I can try and find one that does.
I got one.
You sure?
Oh yeah, I'm all set. Besides, it's more fun this way. All right. We're ready. Those in the front row are in shape today. All right. I don't need the screen. You can get rid of the screen. All right, folks. First of all, you have an opportunity this week, Thursday. After looking at the materials this weekend, I've decided we'll do the rest of the chapters on this test. We're going to do the rest of the book on this test.
That'd be fun.
Thank you. I'm trying out for the comedy night. Is it working? Never mind. Don't answer that. It was just kidding. All right. I will not, K-N-O-T, not be putting thermodynamics on this test. So it is, I can do quite a bit with buffers and weak acids and bases and KSP and KF and titrations. I don't need to do the stuff on thermodynamics. Get everything out of the way here. So, your test on Thursday will be on acids, bases, buffers, KSP, KF, indicators, equilibrium, everything you can imagine with regards to equilibrium. Okay? So no thermodynamics. That help, Amelia? Okay. You're welcome. So we're going to start by talking about indicators today. Since we haven't talked much about indicators, we're going to talk a little bit about indicators. And we have to make our own indicator. So we have a little cabbage here. I think this is old. I think, Victor, remember when I did this last fall? I think this is the half that's left from when I bought it last fall. November, so, yes, it's about that old. Ew, yuck. This is just red cabbage. Sorry, I'll try not to throw too much at you. Don't worry, I won't splash. Never mind. I just stopped at Dave's on the way in this morning and picked this up. So this is just ordinary, normal red cabbage. Most vegetables that have any kind of color associated with them are acids and bases. Indicators that are used in acids and bases, just a second, are also acids and bases, yes? Well, it's on acids, bases, buffers, KSP, KF. You know, it's cumulative since chapter 1. Every test is cumulative, so no, it's not just chapter 17. It's not on 18. So, does that help? All right. So as I was saying, indicators, those things that indicate whether or not you have an acid or a base, are simply compounds that are themselves weak acid and bases in and of themselves. So we're just going to take a little bit of red cabbage here, and that should be enough. Mix it up. I need some water. You know, when I used to do this, it always said cook the cabbage, and after you've cooked the cabbage, sit there and let it sit for a while. And I said, that's far too much work. I'm not that patient. Where's the high speed? There we go. Anybody got a credit card? We'll see if it'll blend. Never mind. Will it blend? If you haven't seen Will It Blend, go check out Will It Blend. All right. This indicator gets to be a little chunky. So, there we go. So we'll strain out the bigger parts. We don't need the big parts. And what we're left with stinks, first of all. It smells like cabbage up here at the moment. I don't know why. You'll have to talk to a biologist about that. The worst part is I usually leave this sit around for about a week. And it's usually sitting in the back of the lecture hall. But so by the end of the week, wait till Thursday, those of you with the test in here. I'll try to remember to take it with me. All right, we don't need it quite that concentrated. We'll dilute it a little bit. There we go. We now have our indicator. Nice, pretty purple stuff. What's its pH, by the way? You all know the answer. What's the pH? 7. It's just water. I mean, there's water in here right now, so there's a pH of 7. There's a great exam question that says, what happens if I cook this and it changes color? What is happening chemically? You're not breaking anything down. You're just changing the pH when you heat it up, because the Ka is dependent on temperature. So as you heat this thing up, it's going to change color. So you may want to pay attention to the colors today. So we now need some of that indicator. And hopefully I can see well enough. I'm not going to use this. All right, we'll start with something we know the pH of. Vinegar, common household vinegar, 5% acetic acid by law. So we take a little bit of vinegar. That looks like enough vinegar. And, ouch, I'm going to cut myself. And we take a little bit of our cabbage juice indicator here. And we squirt it in there. We need more. I always was a little impatient. Ooh, color changes. In this nice weak acid solution, we have a nice, very pretty pink color. So we'll put this way over here on our acid-base scale. Oh, actually, let's just take part of it. So there's our acid. And we will add a little sodium hydroxide to it. So we'll add a little bit of strong base to this. And we'll see what happens. Did you pick that color? He had it predicted. All right. You've seen this before, haven't you? No, never. It's a nice... Oh, look. It's purple. I wonder what happened. I think I neutralized the acid and got it back to a neutral solution. I just did a titration, folks. Let's titrate. Oh, you like that, huh? We'll do a little bit more. There, we now have a basic solution. Why is it important to swirl your titrations when you do them in lab? Because they don't always react completely until you've mixed it up. And so now we've got it in a very basic form. Oh, it's a little warm too. I wonder if it's an exothermic or endothermic reaction. All these observations you can make now that you know about them. All right, so in our acidic form, we have this pink solution. In our neutral form, it's purple. And in our basic, it's green. If I try it again, except this time, I want to use this one. Ah, here we go. This is the one you're all probably used to. This is phenolphthalein. If you can spell that, you get, never mind, I won't say that. Phenolphthalein is not a hard thing to spell. Phenolphthalein. There, I'm looking at it, I can spell it. If you ever need phenolphthalein and you don't have any, X-Lax. If you ever need X-Lax and you don't have any, just take a little sip of this. It'll do the same thing. So, we take a little bit of acid. Well, let's try a little different acid this time, hydrochloric acid. Let's go with a strong acid this time instead of a weak acid. And just to make sure that the color is right, you can see we still have that nice red color. Compare it with this one. It's a little bit redder, but not too much. So my strong acid's a little bit closer to red than pink. That's okay. Let's try the same thing, though, with phenolphthalein. So we try a little hydrochloric acid. And since I'm going to conserve a little, it's now dilute hydrochloric acid. I have no idea how dilute. I just know it's not quite as concentrated as before. And now we'll take a little bit of this. And hopefully I'll remember which bottle is which. And we add a little phenolphthalein to this. And it got cloudy, but that's about it. It didn't do anything else. It's just cloudy. Well, let's do a neutralization reaction on it. We'll take a little bit of 2.5 molar sodium hydroxide. The hydrochloric acid, by the way, was 1 molar. So it's 2.5 times more concentrated. And I just used a little bit and diluted it, remember? So we'll add a little bit of base. And all of a sudden we get this bright red color. So now this is a basic solution. I've neutralized that little bit of acid that I put in there. And phenolphthalein, when I started, was that colorless solution. Now in base, and I've gone way past the equivalence point, folks. This is now pink. This is basic. The first lesson is that the color of an indicator tells you nothing about whether it's an acid or a base. The absolute color doesn't say if it's reddish, it's an acid. It depends upon what indicator you've got. In the case of phenolphthalein, it starts out as a colorless solution in acidic solutions. And when you neutralize it with base, when you make it basic, you get this beautiful pink solution. If you've ever read the magic water to wine to beer to milk, that chemical demonstration starts with an acidic solution with phenolphthalein in it, and it neutralizes it by adding base, so you get wine now. Then they convert this into beer by making it brown, and then they make it milk by precipitating out a white solid. And so the chemistry that goes on there. So here's another basic one, but it's pink. Now those of you who've used indicators before, you can write the equilibrium for any generic indicator by the fact that it is itself a weak acid. And so we'll symbolize indicators as their acidic form is HIN and their basic form is IN minus. In the case of phenolphthalein, you have an indicator that is colorless in acid solution and red or pink in basic solution. Mary. Can an indicator be a weak base? Sure. It can be a weak base too. So it can undergo the same kind of reactions as a buffer. Okay? It has both the acidic form and the basic form that are both in there. And the color that predominates is going to depend upon what the pH is. If you've got a high H3O plus concentration, in the case of phenolphthalein, you've got a lot of products. Le Chatelier's principle, which we talked about many moon ago, pushes this reaction back to this side. H3O plus is a strong acid, so it's going to force this reaction over to this side of the equation, and you'll have the colorless form of the indicator. When you start to neutralize the H3O plus, you start to get relatively equal amounts of these. And eventually you'll have an excess of the base form of this, and when you have the excess of the base form, when IN minus concentration is much larger than HIN, it will be the basic color. In the case of red cabbage, over here we've got pink. Over here we've got yellow-green. And in between we've got purple. So if we've got about equal amounts of them, if we're at neutral pH, we can get the purple color. You can get just about any color you want. Let's see if I can do this carefully. Goggles, there they are. So we need a little bit of vinegar. So we start with some vinegar, which is about 10th molar acetic acid, by the way. We add a little bit of indicator to it. And then we take a new dropper and some sodium hydroxide. And now we'll do a titration. And this is all a titration is. Start with a solution of a certain that we have a certain pH, and we start to neutralize it. And so we add some base to it, swirl it around, and see if we can get the color to change. At some point, the demonstrator says, you know what? This is moving too slow. Let's see if we can lighten it up and get a lighter pink color. Lighten it up a little bit more and get a light purple. Why do I get flashes of green in there, by the way? Green is over here somewhere. Why do you get flashes of green? In the vicinity of where you add the base, there's a high concentration of base, and so the color of the solution will take on that high pH. As you swirl it around, it mixes with everything else, and you start to get the color back that it really is, so that when you first add it, you'll get a flash of color, And those of you who've done phenolphthalein titrations will see that you get that red showing up. The challenge is not panicking and saying, oh, I've got to slow down. You can actually keep adding it very quickly. Or have it stirring. And as you can see, we can get this to the light purple, to a light green. I should have worn the white lab coat today, which goes back to purple again. And if you're very careful, the color lasts longer every time you add it. It takes longer to mix it until you go too far, and you can see now we're somewhere in between. We're not quite as bad as this one. This one's now yellow. Now we've got a green. We've got a pH somewhere over here. So if that's a pH of about 2, this is a pH of about 12, that one's somewhere in between. It's not quite 7 because 7 we said was purple, so it's somewhere beyond that. Now, this is where people say, wow, why would you do that? This is bromothymol blue, and this one is phenol red. So we want to take a little bit of acid. I can just see that spilling. That's all right. I did this in a hotel once. They had brand new carpet. I had concentrated sulfuric acid. Take concentrated sulfuric acid in organic lab next year and see what happens when you mix organic esters with sulfuric acid. It is not a pretty smell. The hotel was not real happy with me. This one is the bromothymol blue. We put a little bromothymol blue in this acid solution. And nothing happens. All right, we'll try a little phenol red. Oh, that one's nice. I like that. It's red, and we add it to the acid solution. I'm going to have to dilute this one a little bit so you can see it. We'll add a little bit more to make the color stand out. There we go. Phenol red is this nice golden, yellowish orange. You probably can't even see it in the back. It's so faint. This other one, the bromothymol blue, is colorless, just like phenolphthalein. And now we take a little bit of base. This is the bromothymol blue again. Add a little bit of base to it. And we find out that this is so concentrated I can see all the base in there and I can't see any color. It tells me that bromothymol blue is no good. There's no color change in this. I wouldn't use that thing for. Let's just see if it's indeed basic. Oh yeah, it's basic. I don't know what happened with the bromothymol blue. That's what happens when you take it off the shelf and don't know what it is. I would say that we could get rid of this one. Matt, if you're here, you can toss that one. Let's try this one. This is the phenol red in acid. Add a little base to it. And again, you get the color change to red. This is one where you're watching a color change from yellow to red. When does it change color? If you're a red-green colorblind, as what, 1/6 of the male population is red-green colorblind, or something to that effect, they won't see this one. Okay. If you've done titrations in class, in high school or somewhere before, you probably used phenolphthalein. It goes from colorless to pink. And the reason why you use this one is because the color change is so obvious, even if you're colorblind, you can see it. It goes from one shade of color to a different shade that you can tell when it's changed. You tend to go way past the endpoint like we did here, but it's okay. Now my question to you is, why do you have different indicators? Why would you want different ones? I'm sorry? The color change? occurs at different pHs. So every indicator is going to give you a different color change for different pH. This is a universal indicator. It changes color at every different pH. There's a slightly different shade. And so you can use this one for pH paper. pH paper is just paper that's been coated with a universal indicator, and red cabbage is actually one of those universal indicators that you can use. Is that because it's a pH of 7? No. It's a universal indicator because it changes color at different colors at every different pH. And so I've got a range of colors from reddish pink to yellow green with purple in the middle and everything you can imagine in between. So every pH is going to give you a different color. Is an indicator itself acidic or basic? The indicator is a weak acid. So does it have a pKa? Yes. So if you want to pick an indicator to monitor a specific pH, and actually they're hard to find, but you can get not pKa's because they don't list them. They list them as PHINs. In other words, what color does it, or what pH does it change color at? What is the ratio at which the concentration, when they're equal, you're going to have the neutral color, and when you have the predominance of the base, you have the basic color. If you have the predominance of the acid, you have the acid color. And it's just like a buffer. The ratio is 10 to 1. If you've got 10 times more HIN than IN minus, it's going to have the color of the acidic form. If you have 10 times more IN minus than HIN, you're going to have the basic form. If you're in between, you're in the transition range. And so which indicator you pick, if this is my titration curve, I can pick an indicator that changes color here, here, or here. Those are just three. It ends up there's lots of different indicators with lots of different pH ranges. The indicator you pick depends upon what you need. As we said about a week ago, if you need it to stay acidic, pick an indicator that's going to change color closer to a low pH than a high pH. If you need to make sure that it stays neutral, pick an indicator that's going to change color at pH 7. Now the book talked about it and we went over it quickly. The difference between equivalence point in a titration and endpoint in a titration. The equivalence point is where you've added an equivalent amount of acid to base or base to acid. So the moles of acid equals the moles of base at the equivalence point. The end point is when you stop the titration. In the case of phenolphthalein as your indicator, it's when it turns pink. It's not the equivalence point. If I take this same titration curve and I take the derivative of this titration curve, so I'm going to plot change in pH as a function of volume. Those of you in your calculus class, it goes from concave up to concave down. So, putting it so you can see it. It looks like this. The equivalence point is there. It's right where it changes direction, the inflection point of the titration curve. Nope, not a question in the back? Okay. So you can figure out the equivalence point when you've got exactly the same amount of moles of acids and base. In the case of phenolphthalein, if you use phenolphthalein as an indicator, your endpoint in a strong acid, strong base titration is here. That's the pH, or that's the place where phenolphthalein changes color. You're past the equivalence point because this is phenolphthalein here. It's at a high pH. So when you calculate the number of moles of acid based on the number of moles of base that you've added to it, if you use phenolphthalein as an indicator, you've gone too far. Why do we not care? Why is it okay to use phenolphthalein to teach someone how to do titrations? A, the color change is easy to see, but if you're past the equivalence point, why would you use it? Why doesn't it matter? Anybody want to hazard a guess? If I do a strong acid, strong base titration, that's the shape of the curve. That's where phenolphthalein changes color. It's about pH 8.5 to 9.5. The equivalence point is at a pH of 7. So you're 1.5 pH units past the equivalence point. Why doesn't it matter? Because the amount of base you add at that point is such a small amount, it's a fraction of a drop, that it doesn't matter. If you're doing a titration with a strong acid and a weak base, this curve is going to change. The first half of the curve, because you've got a strong acid, is exactly the same as a strong acid with a strong base. The second half, though, now the weak base, once you've neutralized all the acid, now the weak base takes over. So if I've neutralized all the acid, and this gets back to buffers, if I mix HCl with ammonia, there's a problem in your textbook that says, okay, take the following three solutions and calculate their pH. And the three solutions are 25 milliliters of 0.1 molar HCl, with solution 1 has 25 mils of HCl, 0.1 molar, and 10 mils of ammonia, 0.1 molar. Solution 2 is equal volumes of the same concentration. And solution 3, that's right, we could use this. I really should just come in time sometime and use Butler's notes for class. And those are the three solutions. On this curve over here, if I start with 25 milliliters of HCl, my initial pH is down here. It's 10th molar, its pH is 1. Doesn't matter how many milliliters I've got, its pH will be 1 if it's 0.1 molar. Now I start adding base to it. I'm neutralizing the HCl. When I neutralize HCl, an acid, with ammonia, a base, I'm not even going to worry if it's strong or weak right now. When you neutralize an acid with a base, what do you make? Water. So I'm making water. So I take that HCl, I neutralize some of it, but what's my limiting reactant? If I've got 25 mils of 10th molar HCl, I have 2.5 millimoles of HCl, and I've got 10 mils of 10th molar NH3, I've got 1 millimole of ammonia. So 2.5 millimoles of HCl, 1 millimole of ammonia. My limiting reactant is the ammonia. It gets used up. I have excess HCl. Is the solution going to be acidic or basic? Acidic. I've still got 15 milliliters. I've neutralized 10 of it since they're the same concentration of excess HCl. Or I've got, if you prefer, what did I start with? 1.5 millimoles of HCl. But now the volume is 35 milliliters. So here, I could calculate my concentration of HCl by taking the amount of HCl in the volume, and from that I can get a pH. On this curve over here, I'm still over here somewhere. I've still got a very acidic solution. The strong acid is determining the pH of this solution. If I add another 2.5 milliliters, I've made a buffer. If you want to make a buffer, there's 3 ways, and one of the ways is start with an acid and a base and neutralize half of it. All right? This one. Now I've added 2.5 millimoles of acid and 2.5 millimoles of base. I'm now at the equivalence point. There's an equivalent number of moles of acid to base. It doesn't matter that one is strong and one is weak. The number of moles of acid equals the number of moles of base. Is the pH going to be acidic, basic, or neutral? Why? What did you make? When you neutralized the strong acid with the weak base, you made ammonium ion. Ammonium ion is a weak acid. And so your pH at the equivalence point is still going to be acidic. You've neutralized all of the strong acid with weak base. You end up with a weak acid. It's still acidic. Did we make ammonium ion in step 1? Yeah, we did. We started with HCl. We added ammonia to it. When you neutralize the HCl with the ammonia, you make water, but you also make ammonium ion. Why didn't we care about the ammonium ion in determining the pH of the solution? Because the HCl is strong. If I mix a strong acid with a weak acid, the strong acid will determine the pH, unless its concentration is so low that it's not going to contribute. What's the pH of 10 to the minus 8 molar HCl? If I've got HCl that's concentration is 1 times 10 to the minus 8, its pH is, please don't say 8. 7 minus a small amount, because it's an acid. It's a strong acid. It better not be a basic pH, right? If it's at 25 degrees C, Allah thinks it's 8. It's 6.97 if you do the calculation. In this case, the ammonium ion's not going to contribute enough to change the pH. So at this point, when we're at the equivalence point, we're going to have a pH, if I remember right, it's 4.74. And then past here, now when we're at the third part of this, at this stage of the titration, and that's all this is a titration, we've added 35 milliliters or 3.5 millimoles of ammonia to 2.5 millimoles of HCl. We're past the equivalence point. We still have one millimole of ammonia more than I need, but I also have 2.5 millimoles of ammonium ion, because I neutralized all of the HCl and I made ammonium ion. Is this solution acidic, basic, or neutral? Just a second, Emma. Is that solution going to be acidic, basic, or neutral? Let's see, I've got 1 millimole of a weak base and I've got 2.5 millimoles of a weak acid. I have more acid than base. It's still acidic. Just slightly, but it's still acidic. Emma? Yes. The easiest way to approach these, as we talked about last week, because the question is always, what's the equation, is as soon as I see ammonia in the problem, and I recognize that ammonia is a weak base, better quit smoking, Amelia. I said you better quit smoking. Ammonia plus water gives me ammonium ion and hydroxide ions. Equivalently, if you've got ammonia, you also have ammonium ion. So you could start with ammonium ion and react it with water to get ammonia and H3O+. The reason why I'm encouraging you to write both of these is because now when I come over here and I say take 25 milliliters of a strong acid and mix it with 10 milliliters of a weak base, I look at my two buffer equations, and we showed on Friday it doesn't matter which one I use to figure out the pH of the mixture. I'd say, oh look, ammonia reacts with strong acids, and they react 1-to-1, and they make ammonium ions. And so when I have to say what equation am I using, I'm using the acidic form of the buffer equation to figure out what reacts with what. That's the limiting reactant problem. As soon as you've solved the limiting reactant problem, you can do the buffer problem that results, because now I've got how many millimoles of this? 1.5 of excess ammonium ion in 35 milliliters. I've used all this up, right? If I'm looking at solution number 1, excuse me, I've got 1 millimole of ammonium ion in 35 milliliters. I don't care about this. I used all this up, but I still have what? One and a half millimoles of that. Everybody see that? If I go back to solution 1, I used up all of the ammonia, so it's gone. It was the limiting reactant. I made an equivalent amount of ammonium ion, 1 millimole. It's in a total volume of 35 milliliters. I have excess hydrogen ions. You have to recognize that HCl is a strong acid. So I have excess of this. And so if I solve this equilibrium problem, which direction is this going to go? Left to right or right to left? It has to go left to right. There's only one reactant if this was the reactant side. There is no ammonia, so there's nothing for H3O+ to react with, so it can't go this way. There's always water, though. So there's my equilibrium table. Ka, it ends up, I'm not even going to worry what the value is for Ka, is going to be X times I'm not going to worry about units right now, taking a shortcut. And if we solve this in the normal way, we're going to assume X is much less than 1 over 35. If X is less than 1 over 35, what's true here? It's also much less than 1.5 over 35. So this term and that term effectively cancel each other. Oops, sorry. They don't. I don't want to say that. They do, but I don't want to say that. I don't want to solve for x is my point. If I assume x is much smaller than this, then whoops, too high. H3O plus. What's going on here? 1.5 over 35 is the H3O plus concentration. When we just talked our way through it, we said the concentration of HCl is going to determine what the pH is. The ammonium ion is not going to contribute to it. Anytime you have a strong acid with a weak acid, the strong acid determines the pH. Well, the equilibrium table told me the same thing because I'm going to ignore this X here. So my hydrogen ion concentration is just 1.5 over 35. All right, at the equivalence point, then what do I have? At these two, this is the equivalence point now. You've added an equivalent amount of acid to base. If I fill in my table now, let's see, my limiting reactant here, they both get used up. So I have what, 2.5. I've got 2.5 millimoles in 50 milliliters, right, of that. But those both got used up. I used up all the HCl. I used up all the ammonia. All I have left is ammonium ion. And so this is at the equivalence point. Your question was, is this true at the equivalence point or the end point? It depends upon what indicator you're using. The end point of a titration is when you stop. And hopefully you stop at the equivalence point. But you usually stop when the indicator changes color. If the indicator changes color at a pH less than the equivalence point, then you still have some excess acid. If you stop at a point where the indicator is already in the basic form, like with phenolphthalein, then you've got too much base in there. You've gone past the equivalence point. The only time it matters is if you're doing a weak acid or a weak base titration. In a strong acid, strong base, that change is so sharp that I can pick any indicator I want along that vertical slope. And so I can use phenolphthalein because it's easy. I can use phenol red because I have it. I can't use this stuff because it didn't change color. Or you can just go buy some indicator. All right? I will see you Wednesday. We'll do problems Wednesday and review for the test. If I add water, will I push it that way? No, because the concentration of water won't change. The concentration of water is already constant. So we ignore it. That's why it won't matter.